545 people today have gone to a UK hospital because of a cardiovascular complaint. 420 of whom have actually died because of the same complaint. 1 in 10 of us here will develop osteoarthritis, and if you're a woman, that number goes up to 1 in 3. Now that sounds a little bit scary, but let me throw some other statistics and likelihoods at you. Most of us will experience an abrasion at least once in our lifetime. And if you're a child, then that likelihood goes up. Most of us will also have experienced what's known as delayed onset muscle soreness, which comes from essentially straining your muscles and tearing apart the tissues, which happens after strenuous exercise, or in some other people's case, as is with mine, after a month of lounging around and doing virtually nothing on holiday. In all of the examples that I've described earlier, the one thing that's common is that there is damage being done to the body. But in the examples where we could just laugh it off, the important thing is that there was repair and regeneration. I'm Malavika Nair. I'm a third-year PhD student at the Department of Material Science, working with the Cambridge Centre for Medical Materials, and I work on ice-templated collagen scaffolds for tissue regeneration. And this is a song of ice and collagen. It is a brief introduction into how two seemingly unrelated concepts can come together to actually pioneer an area of research that can enable regeneration and repair in human tissues. So to start with, what is a scaffold? So a scaffold in the traditional sense, as we know, in the sense of buildings, is basically a temporary structure that is put in place that provides structural support for the building, and that also enables construction workers to weave through and allow ease of access to their equipment while they're making the repairs. Now, a regenerative scaffold isn't much different from these traditional scaffolds. The only difference being that instead of the construction workers, we've got cells doing most of the work. So, in a sense, what we need for a regenerative scaffold are the same kinds of requirements. We need them to be able to deliver the cells to the site of repair. We need to be able to ensure that it's a temporary installation, so it is bioresorbable, it degrades away, it metabolizes away at the end of its lifetime. We also need to make sure that while it's in place, it provides the necessary structural but also functional support for the tissue that we're intending to repair. So with all of this in mind, we can think of a porous interconnected scaffold, and this is a micro-CT reconstruction of one of those, that can serve to address some of these issues that we've come across here. So why collagen? Now, collagen is one of the most ubiquitous proteins in the body. It forms about 97% of all human connective tissue, and perhaps the most exciting thing about it is the fact that it is found in tissues that are so different in their function and their structure. So it is found in the bone, the cornea, the skin, and the heart. Some that are really hard tissues, some that are squishy, but all have different purposes. And from the perspective of a material scientist, what's really exciting to me is that there is structure that you can vary on different length scales, all the way from the molecular length scale, where you can change the amino acid sequences, up to how these fibers can form together to form different bundles and different properties from there. So in nature, what we find is that the properties of cornea versus tendon differs because of the composition of the amino acids at this level, whereas the tendon versus skin is because of the way in which these fibrils are packed in the tissue, where the skin tends to be more random, whereas the ones in the tendons tend to be more aligned because of its requirements for structural integrity. Now, how do we create a collagen scaffold? It's actually quite a simple pipeline that we have. We start with collagen, which is a byproduct of the meat industry, or you can even get it from seaweed, and we essentially blend it with acetic acid. So once you've blended it, you've got a suspension, and you put the suspension in a freeze dryer. Now we'll explain a little bit more about what the freeze dryer does in a second, but in goes the collagen slurry and out pops a collagen scaffold, which is essentially a little sponge, a little cake of collagen that's mostly empty space. We can then cross-link it or do various other post-treatments of this scaffold to give it the structural and mechanical properties that we desire for the site of repair. So what is freeze drying? Freeze drying is essentially a neat way of dealing with how we can get from a collagen protein that's fairly fibrillar, it kind of exists like a powder almost, into something that has a defined and controllable structure. And it's all based on ice, it's all based on water, and that's kind of the crux of this talk. So we start with collagen slurry, which is essentially just a bunch of molecules of collagen floating around in a sea of water. And we drop the temperature, so we freeze it. Now, something that's quite unique about ice is that unlike most other solids, it's very intolerant to any impurities being part of its crystal structure. So water, for example, is very tolerant to solutes. We know that we can put sugar in it, we can put salt in it, and it's still a solution. It doesn't separate like oil and water does. But in this particular case, ice will not accept anything that's not H2O, or it will accept very trace amounts of it. What that means for the collagen is that all of these molecules of collagen can concentrate around the ice crystals that grow. Now, when they concentrate around these ice crystals, they're essentially packing around and forming a network around the basic shape that the ice crystals create. So the ice crystals are essentially acting as a negative mold for what will become the collagen scaffold. So that's all well and good, but how do you get out the ice at the end of it? Because all you really want is the collagen. And that's where the sublimation process, the drying process, comes in. Because if we just put the temperature back down, we'll just get the collagen slurry back, and that's of no use to anyone. So the sublimation process essentially involves taking the ice crystals from the solid phase directly down into the gaseous phase, and thereby completely bypassing the liquid phase in the middle. By doing so, we are essentially left with what is a porous, interconnected, open structure for cells to percolate through and actually traverse the whole structure and lay down new tissue. Now, this is the basis for creating a collagen scaffold, but how can we modify it? So, coming from the perspective of a material scientist, we can modify the structure to modify any properties at the end.
So once you brought it back to room temperature,
yeah.
and now you've got the porous scaffold, is it squishy?
It is very squishy. In fact, it's 99% air most of the times and only 1% collagen, so it's actually very delicate. But we can improve its mechanical properties using the post-treatment processes that we talked about earlier. So back to structure, we can actually change the structure of these collagen scaffolds at different levels. If you think about it, essentially you do need to put it at the site of injury, and these sites of injuries can be millimeters to centimeters in scale. So we need some way of being able to direct the structure at that level. But we also can affect the level of the molecular structure, the amino acids, the various other biochemical markers that are present on the collagen, to be able to direct cell growth through a biomechanical cue. That's all well and good in practice, but what that means in the lab is that you've got a whole list of additives and a whole list of parameters that you can play with. And as we discover new ones, the parameters just grow exponentially, and it gets increasingly difficult to actually understand what to do and how to get control over this. So to distill this, we can essentially say, how about we just consider what aspect of the entire process gives rise to these structural attributes? And then we can say that the top two, the macrostructure and the microstructure, so that's millimeters and micron levels, so 10 to the minus 3 and 10 to the minus 6 meters, are determined predominantly by the ice, and anything lower than that is predominantly determined by the collagen. So there we begin, volume 1 of our journey into the song of ice and collagen. Ice. So ice, as you may know, is quite ubiquitous. It's very easy to freeze. You just need somewhere that's relatively cold. But what's also especially interesting about its structure is that it forms these tree-like shapes. So these are called dendrites. Now, having these dendrites are actually quite useful because instead of just freezing something as one solid block, if you froze them as these tree-like structures, what you get is that these channels can connect to each other. And that's necessary because if you're putting cells through this empty scaffold, you want the cells to be able to go from one channel to the other. You don't just want them to plop straight through. We can use a tube for that. But how do we actually manage to control the structure of this ice? Now, I don't know if you've heard of this, but snowflakes are said to be extremely unique. Now, snowflakes and ice are slightly different because snowflakes are grown from vapor, whereas ice is actually frozen from liquid. But the reason why they're said to be unique is because you can't exactly replicate the conditions of growth that they're in. But we can, for the most part, with ice. So this is an example of how we can control some of the pore structure in our collagen scaffolds through the conditions of ice crystal growth. So over here we've got two examples. So we've got liquid nitrogen over here and dry ice and ethanol. So liquid nitrogen freezes at minus 196 degrees Celsius, or 77 Kelvin if you prefer that. And essentially what it allows is for an instantaneous cooling of the ice. So it allows a temperature gradient to be established that's actually very linear. And that's essentially what you get in these structures that form. You see really aligned pore structures, which is essentially a remnant of the really aligned collagen grains that formed. On the other hand, if you use a slightly higher boiling point solid or sublimation point of solid, like dry ice or ethanol, you can get a little bit more variation in the temperature gradients that you see. So as you know, you exist in an area where your core temperature is very different from the environment around you, but if that were closer to equilibrium, or if you weren't able to establish such a gradient, then that's what will happen with the liquid nitrogen. But that's not the case when it's with dry ice and ethanol. You get some variation in the temperature gradients. And so what you get is a structure that's a little bit more wavy. So I think it's a little hard to see from there, but I guess you'll just have to take my word for it. It comes off as little branches that go off the side rather than just straight through along the direction of the temperature gradient. So that's good, because what that means is that we can affect the directionality of these pores at the macrostructure. So if we need something to be spiraling, we can get it to be spiraling. If we need something to be perfectly aligned, say for nerves, then we can get it perfectly aligned. But what about the shape of it, the actual size of it? So naturally, if there's a tube that you can't fit into, there's no point to having it really tortuous and really interconnected. So it turns out that the size of these actual pores is determined predominantly by the temperature at which you freeze. Or equivalently, you can say the amount of time it spends at 0 degrees. So that's the freezing point of ice. And this is one of the curves that kind of represents that. It basically shows that it doesn't matter what other conditions you have in a freeze dryer, what kind of mold, what kind of thermal gradients are established within there, but if you can get the same time at equilibrium, so that's the amount of time spent at 0 degrees, then you can essentially get the same pore size every time. So that's really useful to know, because obviously cells, as people, have different shapes and sizes. So if we want to select which cells are able to go through from a purely structural and purely kind of physical point of view, then we have a very crude first way to approach this problem and actually say, okay, if I want something that's 200 microns large and that's for my blood vessels, then I can select something that has a time at equilibrium of roughly 8,000 seconds. So that's starting to see how some control can be given into the process from a very engineering point of view. And we can discuss the kind of thermodynamics behind this later on if you're interested. But essentially what this translates to is that you get really tiny itty-bitty pores at a really low temperature and really large pores at a slightly higher temperature, which is driven by essentially the driving force of nucleation. So this is basically saying how far away is it from 0 degrees when it first starts nucleating, which means how much of a kick are you giving it to roll down a hill back to equilibrium. So the one thing that we haven't considered so far when considering ice is the process of sublimation. Now, ice growth and the ice crystal growth has been given a lot of attention in terms of the structures that can form, but we gently touched on the meso-structure. Now that's a very wishy-washy word because essentially it just means everything in between. So one form of meso-structuring that we can create is actually as part of the sublimation process. Now this was previously thought to not have any significant effect on any of the structures that form, but one of the things that we did earlier on this year is we looked at the green part of the curve that we'd seen before. So this is where we dropped the pressure. And we tried to see what the effect of the actual pressure to which we stop the curve has on the features of the ice that form. And what we see is that as you decrease the chamber pressure, so this is going from 500 pascals to 100 pascals to 35 pascals, we see that there's some level of meso-structuring, some level of roughening that happens on the surface of these ice crystals. And what's more interesting perhaps is the fact that the roughening, so there's a periodic wavelength that occurs in each of these ice crystals. I'm going to call that lambda 0, and that's actually very characteristic at a given chamber pressure. So what that's really suggesting is that if you can control the chamber pressure, you can create an extra degree of freedom in the roughening and the topography that you can create in these scaffolds. So the eagle-eyed amongst you might have noticed that 500 pascals is actually higher than the triple point of water, and that's exactly what it's trying to show. So you don't get any features at this level because it shouldn't sublime, it should just be ice. Okay, so what it turns out to be the case is that these features actually have a power law dependence. So you can actually get features from 7 microns, maybe 2 microns at the lowest end, if you go really, really low in pressure, all the way up to 25 microns, 30 microns, which covers essentially the range between the larger protein aggregates that you can form with having other additives of collagen to just under what ice should be able to do when you solidify it. So that's essentially where kind of ice exists right now in the field in terms of what kind of structure it can create. So I guess it's time to move on to the other thing that creates meso-structuring, which is volume 2, collagen. Now, collagen essentially determines the same thing, pore morphology, but we're now looking at a different set of conditions. And what it really determines in these pore morphology is not really the size, but now the shape of the actual pore. So it's not really exciting to look at the directionality here or the shape, but rather if you can see, maybe, it's a lot more fibrillar under some conditions. So this is under water, when collagen packs around water, as opposed to when it packs around lots and lots of acetic acid, when it's rounded and it's got a smooth wall. So that's essentially saying that collagen interacts with its environment, which is understandable, but the way in which it interacts with its environment can have an effect on essentially how interconnected the structures are. Yeah?
Do you know if that's because of the fact that it's acetic acid or just because it's acidic?
I can explain that later. I mean, essentially it's to do with the amount of solute and the type of solute and the charge balances. Because as you have pointed out, it's not just acetic acid, you can get the same effect with hydrochloric acid. At the same pH, so that's 0.05 moles of acetic acid and 0.001 moles of hydrochloric acid, which are both at pH 3, you have different solutes and therefore different charge layers and different interaction with the collagen in itself. And you can get the same pore size, but different what are known as percolation diameters, which is essentially a way of saying, if you had a spherical object, what's the maximum size of that spherical object if you kind of extended your network into an infinite network that could traverse all the way down the structure? So that's known as the percolation diameter, or this value of DC. So this one has a DC of 72 microns, and this one has a DC of 32 microns. Otherwise, same condition, just the fact that the solute is different, and that's because it has fibrous pores, whereas this one has smooth, rounded pores. Now, that's all well and good, but what does that really mean? So in a sense, what we're trying to say is that we're trying to use all of these values as a surrogate for doing some actual cell tests. So on the right here, what we see are some fibroblasts that have been seeded on the surface of a scaffold. So fibroblasts are kind of the generic workhorse that you can put in for all of these tests, because they can basically differentiate into other types of cells. So we use them as a marker of how cells would respond and what kind of cells or tissues they would like to become based on the cues presented by the substrate. But what we see here most importantly is the fact that with a higher percolation diameter, we see cells penetrating a lot further down the scaffold than we do with the lower one, where it's basically just sitting on the top of the surface. So these structural parameters clearly have a huge impact on the biological response of these scaffolds as well. The other thing to consider is that we said earlier on that these scaffolds need to have some level of structural integrity. And that level of structural integrity is not going to come from something that's 99% porous on its own, and collagen on its own is relatively squishy. So what we can do is we can do a process known as cross-linking. And this essentially involves changing some level of the structure in between the fibrils. So this is on the angstrom to couple of 100 nanometers level in terms of its extent. And we are essentially saying that if we have a collagen molecule, which we have just put away as col, then we can link every single collagen molecule with an amide bond. So every single crosslink can then extend into a network of crosslinks, which means that you're basically all holding hands, and if one person pushes you, you're still all the more stronger because there's the network to support the rest of the stress. So that's good, but if we're improving the mechanics through this process, we're also changing the chemistry. And even though we do get a tenfold increase in the elastic modulus, what we see is that cells, which generally, especially fibroblasts, they generally prefer stiffer substrates. So what should be 200% cross-linked over here, we should expect to see more cells on there. But what we've done is we've essentially removed all the binding sites that the cells would like to have adhered onto. So it's kind of this process where there's a sweet spot. You don't want to have something that's so weak that if, let's say, you put it in the heart, it fails because it can't withstand the compressive forces in the heart. But at the same time, you do want cells to infiltrate it because they are essentially the construction construction workers to do the repair. So what we can do is reintroduce some of that chemistry after the cross-linking process. So this is something that's even more cross-linked. It's 500% cross-linked. And this time we restore the peptides that were missing. So if you're particularly interested, it's the GFOGER sequence, which is particularly important to any anchorage-dependent cells. And what they do is essentially all of the effects that we'd lost from not having from having the cross-linking, we still regain because we still have something that's really stiff, but now we've also got the cell activity because it's quite happy to adhere onto the peptides that we've put on the surface. So you kind of get the best of both worlds. You've restored the chemistry and the mechanics are pretty good on its own. Okay, so what's next? I guess the idea is that with all of this in mind, we can try and build a cell niche. We essentially have, as I mentioned before, a fibroblast, which is a pretty generic cell. And we want it to be able to sense the environment around it and do what it does best, which is either wound healing or creating new blood vessels, or even just generating new tissue on its own. So tooth eruption is one example of it, but so is chondrogenesis, which is if you want to create new cartilage, for example, or the cells around it. But all of these are very, very different structurally, and we have to provide the correct biomechanical and biochemical cues in order for it to be able to do that. And the idea is that given all of the elements that we've put together from the ice and the collagen, we can hopefully start to build something that looks very different, but covers all these aspects for different purposes. So whether that's seeding cells onto a membrane so that we can have a dermal graft or a graft for really squishy cartilage, or whether that's actually filling it in with bone mineral, which is a lot harder, a lot stiffer, so that it can support the weight of the body and regenerate any cracks in the bone. But also, equally, Rob's here, so I'm not going to talk too much about that, you can try and create nerve grafts. So you can create conduits for nerves that allow both conduction and regeneration and repair of neurons. And finally, you can also create a little band-aid for your heart. So in case you do end up with damaged tissue around the heart, having a patch should be able to repair it over time. So I guess really the point of all of this is that we talked about all the things that went wrong, all of the terrible examples. But wouldn't it be nice if one day we can think about all of these degenerative diseases that we talked about, the 554 deaths, and that was no longer a thing, because just like how you'd put a band-aid on your finger, on your skin, you could just put a band-aid in your heart. And that's essentially what the crux of this is. We're hoping essentially that by manipulating things in the physical sense that you wouldn't really have thought of, that you could one day change virtually any tissue and help it to regenerate. So that is it from me. Thank you for listening. I hope that was semi-informative, and I guess you can ask me any questions now.